Good afternoon, everyone. Good afternoon, everyone. I welcome you all to last lecture of this session, which will be delivered by Professor Rohit Mehra on natural radioactivity for health risk assessment. I invite Professor Rohit Mehra to deliver his talk.
Thank you, Abhishek. Slides are visible.
Yes, sir, they are visible, sir.
They are moving also.
Yes, sir.
Yeah. So, good afternoon, all of you, and once again, I welcome all of you for this last session of the third day of a GIAN program, and I hope that you might be learning a lot from the experiences or the talk shared by Dr. Tokonami, because he is having a lot of expertise in the field of assessment of natural radioactivity. And just to fill up the gap, it is my duty as a coordinator to give one or two lectures also. And tomorrow, I just want to inform all of you that tomorrow's total session will be taken by the Dr. Tokonami, and after that, the last day we will be starting with only the first half, that is from 10 to 1 p.m., where we have planned that you will be given a demonstration also, and you will be given hand-to-hand experience of measurement of just a minute. Yeah, measurement of uranium concentration in water samples. So we have arranged one practical demo for you people. And apart from this, let me briefly tell you that you will be given one test also, because that is a mandatory requirement as far as the GIAN is concerned. And I request all the participants to please join the Google Classroom also, because your feedback you have to share through that classroom also, and even you could submit your suggestions on the Google Classroom by writing your suggestions on a piece of paper if you are interested. But still, there are some columns in the feedback form. But if you want that you could further submit some suggestions, you are welcome, so that the next time if we could plan this type of activity, what sort of improvements you suggest that these should be included or these should be excluded. And let me make it very clear that sometimes it seems that a few things are repetitive in nature. The reason for this is like, though we are having a planned course in such a fashion that we can give you a crux of different ideas, like measurement of natural radioactivity in air as well as in water as well as in soil. But we have focused, or we have done a lot of emphasis on the particular topic, especially the air and the soil component, and water we will be giving you a live demo also. The reason for it is like, once as a researcher for this assessment of natural radioactivity, one should be very particular in having an idea that how to prepare those samples, how to calibrate those samples. Even yesterday when I was discussing, you should know what type of energy parameters you are interested in. So in today's talk, we will discuss those things in detail. It will be the extension of my yesterday's lecture. So just this slide give you an idea about the radiation and the life. You can see that radiation is not a new thing. It was present since the Mother Earth, the birth of Mother Earth. So starting from this picture indicates, starting from 50,000 BC, I have mentioned at 2000 AD, you could see a drastic improvement in the mankind, but radiation is same. So we are under the continuous influence of radiations. Now, what are the basic effects of radiations on you people? So, generally, once we measure the effects, because like I was telling you, that this talk is basically giving you an idea about some of the terms which we are using in radiation measurements. Like yesterday, we discussed why we measure in becquerel, why we measure in gray, why we measure in sieverts, why there are different units for the assessment or measurements, though they are interconverted also. So similarly, you should understand what are the effects and what are the types of effects which we could see with our naked eyes, or sometimes we could see after prolonged exposure. So to tell you a story about it, like I visited one of the scanning center of my district, and for some scanning purpose, CT scan purpose, and I asked the person who was operating the CT scan machine that where is your pocket dosimeter? So he asked me, sir, how do you know that I have to wear a pocket dosimeter? So I said that I am basically working in this area, so that is why I know that the pocket dosimeter is very important while you perform these type of X-rays or CT scans on the patients. So he said that recently we had a call from the AERB people also. Like there was a problem with our dose calculations through that dosimeter. So I said, why? He said, actually, I have put my pocket dosimeter under the uh, uh, a tray of the patient tray where the patient is lying in the CT scan, and then continuously for whole of the day, for so many days in a month, that dosimeter goes inside the CT scan machine, again comes out, again goes inside, again comes out. So it was having a very high doses recorded. So then I said, then what is the use of wearing those doses if you don't wear a pocket dosimeter in your pocket? Because it is for you. So it is very important to make the people understand that the dosimeters which have been developed or which has been given to the radiation workers, they are very important and they should be kept along with them. So it's not possible that you keep your dosimeter in the radiation area and then you go home after performing your duties in the radiation fields. So dosimeter will be giving a different reading, and you have been exposed for a particular time, but the dosimeter has been exposed for a particular time. So it is very important to understand the basics of that these dosimeters are very important, especially while you perform any radiation related experiments, or either you work in radiation areas or you work as a radiation physicist in some of the hospitals after pursuing MSc or PG diploma course of radiation effects. Because if you are not aware about the effects, so you can't tell the people that what are the effects of those radiations. So we have categorized the health effects basically into two categories. One are the deterministic effects, that is the severity of it arises with the dose, and for it the threshold is believed to exist. So means you could determine it directly. So like if you go for a say one chart which I have shown you yesterday, that if your dose is more than 700 millisieverts, so you bear hair losses within a span of weeks, 1 or 2 weeks. And this is actually happening once a cancer patient undergoes a chemotherapy treatment. The dose rate is very high. It is around 700 or 750 millisieverts. So that dose rate, once a person is exposed within a 2 or 3 weeks, you could see that he or she has lost her hair. So these are the deterministic effect which you could directly determine. So that is the skin injury or the hair losses are called the deterministic effects. Then there are stochastic effects. So that stochastic effects are not directly, you could say that immediately we could see it, but they are dependent. Basically, they occur randomly, and the probability of effect occurring is assumed to be linear function of the dose with the threshold. So if you see the graph also, the probability of having the effect means if you are having a dose, then directly the effect will be there. Sometimes deterministic effects depends upon the type of the body structure, the type of exposure which you are having. Now, if you see the Bragg curves, this is the Bragg curves which is giving you an idea that how alpha, beta, and gamma basically they are categorized, or how their energy reduces. That is, on the y-axis you could see that dE by dx means if you increase the distance of penetration, how this energy reduces. So you could see from the figure on the right hand side that the specific energy loss along alpha track is around 100% when the distance, of course, we have not mentioned the distance here. So it is around 4 centimeter. So once you have a 4 or 5 centimeters of distance of penetration, the effect is very less. So that means the air or the particles surrounding your detector or surrounding you are the more important parameters which gives you the maximum doses. So if you have a little bit more distance, so your exposure is very less. So we will discuss that thing in our next slides also, where we will be discussing how to keep the radiations at a minimum level. So you could see from the figure on the left hand side as well as on the right hand side that for even X-rays, for even protons, so the doses get decreased when the distance of penetration is increased. Now, the radio sensitivity of different tissues and organs are also playing a very important role in having a deterministic effects on your body. Like the radiation sensitivity which I have mentioned in the table, you could see that highest is there in the gonads, like your testes, your ovaries, and then even in your bone marrow, and the lowest is there in the fats or nerve cells. So if you see from the figure, the direct exposure is different for different organs. The same dose exposed to a given body has a different impact on the different organs. So there are some medium effects on the kidney, liver, lung, and then there are some medium to low effects on the pancreas, muscles, and then the lowest effects are on there in the nerve cells or the fats of the bodies. But your gonadal tissues are very sensitive. Your even eyes, intestines, they are very sensitive for the radiations. So that is why once the radiation occur, so these organs are affected at a higher speed as compared to other organs. So you have to be very careful about selecting the radiation sensitivity. So different organs have a different type of radiation sensitivity. Then radiation carcinogenics. If you see, means what is the cause for different types of cancers which basically occur among the different body parameters. So this left hand side table give you an idea that skin cancer, the cause is X-ray bulb factory workers are exposed to large amount of radiations in the process of their work. So even X-rays could give you the radiation effects in terms of skin cancers. So if you have undergone large number of x-rays, yesterday I've given you some doses also, like if you go for an x-ray, this much of exposure is given to you. So that is why it is very important, which I was discussing yesterday, that our radiation workers or our radiation physicists who are working in the uh, testing laboratories, especially the laboratories where CT scans are performed, MRIs are performed, X-rays are performed, they should be very aware about these things. I had a meeting with one of the radiologist. He said ki we have purchased a 1.5 Tesla MRI machine. So I asked him ki, are you aware about that how this 1.5 Tesla affects our body? He said, I'm a doctor, I need not to go into that detail, but I know it is safe for the patients. Then I said, I will send you some of the literature, and you go through that literature and you will imagine that once a person is exposed to high magnetic field, though MRIs are very safe as compared to CTs or X-rays, but high exposure of MRIs also gives you a very high concentration of radiation damages. He said, how? So then I sent him some of the literature where it was mentioned that if a human body undergoes more than 3 Tesla or 4 Tesla, so then there are very less chances that his water particles or water molecules within the body will regain their shape. So sometimes the damage could be permanent if the magnetic field is more than 6 Tesla. So though with the increase of the magnetic field, the quality of the MRI increases, but still as a radiation physicist, you have to discuss with the radiologist that if we go beyond this much of field, it could affect my body. So for that particular purposes, you should have a basic idea. Sometimes it is being asked by some of the patients or even some of researcher, sir, sometimes we go for CT and sometimes we go for MRI. What is the difference behind CT or MRI? So I'm not going into the so much medical details, but I am just giving you a basic idea that wherever it is a hard tissues or hard bones are there, CT will give you the best results. But wherever there is a fluid type of a material, the MRI will give you the best results. Because magnetic resonance imaging is based upon the dilation of your water molecules within the body. So that is why wherever there is a fluid type of a material is present inside the body, then MRIs are preferred. Suppose if a person has undergone an accident, so suppose he has a brain injury, the best way is to have an idea that whether his skull is safe or not. Skull is very hard. So firstly, the doctor will prefer to go for a CT. So if within the CT he finds some problem, then he will prefer to check the body fluids or the fluid present inside the brain. So there he will prefer the MRIs. So depending upon the type of measurements which you are performing either on the solid surfaces or on the fluids present in the body, so you decide with the CT or the MRIs. So then different cancers I have mentioned that lung cancer, miners in uranium mines inhaled radon by breathing, and then they could be affected with the lung cancers. The reason for it is lung cancer, why it is called by the radon exposure. It is the second largest cause of lung cancer after cigarette smoking. So the second largest cause after cigarette smoking is the radon for the lung cancer activities. Then there are some liver cancers, also there are some exposures. So depending upon different types of risk parameters, so radiation exposures, So you could have different types of effects. Now, objective of radiation protection means how to keep the radiation exposure minimum. So to keep the radiation exposure minimum, of course, one thing is, like yesterday we were discussing, within the dwellings, within the houses, within the offices, you could have a better choice of ventilation conditions. You could have a better choice of building materials which give you lesser exposures. But apart from this, there are some parameters which we generally call as ALARA, that is as low as reasonably achievable. So to prevent clinically significant radiation induced deterministic effects by adhering to dose limits that are below the apparent or the practical thresholds, we have to follow the ALARA. Now, the limit to limit the risk of stochastic effect like cancers or hereditary effects to a reasonable level in relations to the societal needs, values and benefits which are being gained. Again, we have to follow the ALARA. Now, ALARA has a one objective to keep the radiation as low as reasonably achievable. So this is the full form of ALARA also, as low as reasonably achievable. Now, what are the three fundamental principles to keep the radiations as low as reasonably achievable? Is the first is you minimize the time of radiation fields or radiation exposure, which we were discussing, that if you are having a disintegration in a particular room, I will not be affected unless and until I enter in that room. So if my exposure is minimum, if I have no exposure of a radiation field or radiation area, so my exposure will be less. So second is you maximize the distance from the radioactive source. So sometimes if mine workers are there, if some radiation workers are there, or if some radiologists are there or radiation physicists are there who are working with radioactive sources, they could increase the distance. So with the increase of distance, the radiation exposure again becomes lesser. So third is you should use a radiation shielding. So radiation shielding means like you might have performed experiments in your graduation classes also, while you perform some experiments related to the GM counters, where you could keep your sources, alpha or beta sources, within the lead shields. So you might have seen some cylinders of lead cylinders where you could keep your sources and the detector is present within the lead sheet, GM tube is present within the lead sheet, and it is not affected from the background. So you could use some radiation shielding materials. Now, principle of radiation protections, which we were discussing in terms of ALARA. So time, you reduce it, you will get the lesser exposure. And distance follows the inverse square law. So suppose if your distance is 2 meters from the radiation source and your exposure is say X, if you increase it from 2 to 4, your exposure will be, because your distance has increased 2 to 4, that is double. So your exposure will be square, that is 4 times it will be reduced. And if you increase the distance 3 times, from 2, you make it as a 6 meter or 6 centimeter, your exposure will be 3 square, means it will be reduced to 9 times. So distance also plays a very important role, and it follows the inverse square law, means if your distance becomes double, your exposure becomes 1/4. If your distance becomes 3 times, your exposure becomes 1/9. If your distance from the source becomes 4 times, your exposure will be 1/16 times. Reduced exposures will be there. Now, for the shielding purposes, lead is one of the examples, but even yes. yesterday, which we were discussing, fly ash bricks can also act as a radiation shielding material sometimes, because they also absorb so many radiations. But still, the preferable materials are the lead aprons, which we generally wear while performing even some X-rays or other medical diagnostics. Now, the purpose of estimation of radionuclides and soil. So, I will be telling you in details that what type of energies we are focusing, and how we could measure the primordial radionuclides in soil. And basically, we are focusing in three categories: radium, thorium, and potassium in soil samples. And then, like yesterday we discussed, we convert those radium, thorium, and potassium in terms of radium only, that is the radium equivalent, and finally calculate the things. Here we will be discussing the details of that. So if you see the first figure, the soils are collected from the bottom. Actually, what happens if you collect the loose soil or the upper soil? Sometimes the local effects plays a very important role. Suppose you have placed the pesticides, and during that season, if you extract the soil from the upper surface, that pesticide may give you high level of exposure, which actually the soil is not having similar exposure. Like if you sprinkle potash during the agriculture seasons in the agriculture fields, so potassium levels will give you a very high value. So it is preferably recommended that you collect the natural soil at a depth of around say 0.7 to 1 meter from the ground. Then you crush that soil and make it a fine powder, and sieve it accordingly, and keep the temperature less than 40 degrees Celsius. You dry it within the shady area, and after that you make it as a oven dried for 3 hours or 2 hours, depending upon the type of moisture your soil is having. Then you sieve it and finally pack it with particular weight. Like this sample holder is having a 150 gram of weight. So weight also plays a important role, because your detector and the geometry of the detector also plays a very important role. Sometimes we collect 250 grams, sometimes we collect in a marinal beaker, we collect nearly 1 kg of soil. So it depends upon what type of container you are using. So like for this particular container, it is around 150 grams. Then you store those samples to attain the radioactive equilibrium, so that the parent and the daughter equilibrium is obtained, and finally whatever you get, so that is the nutshell effect of the radiations which are causing directly from that particular soil. Now this is the parameter which we are working in, and this detector has a resolution of around 7% for cesium at 262 keV with the activity of 9 kilobecquerel. And you see the efficiency is very less, so but 20%. But generally for radium, thorium, potassiums, its efficiency is high as compared to the cesium. So yesterday we were discussing that you should know for what type of energy you are measuring. So like we were discussing HPG as well as scintillation counter on one day, that for HPG the resolution is very high, and for a scintillation counter the efficiency is a little bit higher as compared to HPG. So why we require the high resolution means, if we want to determine some very nearby peaks, suppose I want to have an idea of an element having energy of the order of 180 keV and another element having energy of the order of say 200 keV. So then quite possible my scintillation counter cannot resolve those two energies. So but HPG though it is having lesser efficiency, but its resolution is very high. So depending upon the type of requirements, either resolution or your efficiency, you could compromise between two different detectors. And if you see from the previous figure, so we evaluate the radium 226, thorium 232 and potassium 40 with the different peaks. One for radium is we generally use 1764 keV of peak with our detector, and for thorium we prefer 2610 keV of peak, and for potassium we prefer 1460 or 1461 keV of energy peak respectively. Then activity concentrations are calculated, and these are the graphs. Actually, if you see the graph, so this is the calibration which we have done with our RG samples. So we know some known standards of soils where the activity concentration of uranium, thorium and potassium. Uranium is basically the radium which we are mentioning. So radium, thorium and potassium is recommended, and by known value of samples we calibrate our detector, and we try to calibrate the peak with the cesium also. So before starting an experiment, the calibration is very important, that your detector's peak, like I know there is say uranium source of say particular energy, say 1763 peak. So I will fix this vertical line to such a value and adjust my voltage and potentials such that this line comes in alignment with the peak. So before performing an experiment, like for thorium, it is 2610. So I will align this line to that 2610 peak. Like here it is 2610, say peak is there. So across x-axis there is an energy, and across y-axis there are the counts. So gamma counts, scintillation counts. So you have to calibrate your detector before performing an experiment, so that with the known source, if you are having a known source, then only you could calibrate, and you have to adjust this vertical line in alignment to the that peak. Now, if you see again the energy spectrum of cobalt 60 and cesium 137 isotopes, it is again corresponding to the different peaks. And like yesterday we were discussing that as a physicist, we should know that how to estimate it. We have to calculate the area under this peak, and finally we have to measure the FWHM value, that is full width half maximum value, so that we could calculate the probability and the activity concentration depending upon the different materials. Now, this is just a particular physics behind that which I am telling you. Suppose at this corresponding to 252 or 256 or 261 keV of peak, there is a peak which is coming. So I have to calculate the FWHM value, full width half maximum value. So I could manually do the curve fitting techniques, or nowadays the softwares are available which do the calculation in such a fashion that they do the curve fitting techniques and finally calculate the area under this peak, and based upon the area under the peak we calculate the activity concentration. Now, the full width half maximum obtained from the experimental work of sodium iodide detectors. So you could see that full width half maximum, we suppose there is a peak corresponding to this value 261. So how to calculate the full width half maximum? Firstly, we have to take the maximum value, and then we have to take the half of it. Here the maximum is around say 15,000 to 16,500. It is around 16,000 I could say. So within the 16,000 I will take the half of the counts as say 8,000, and then I will draw this line. So this is the half H2. So at H2 I will draw again a line, and then draw some corresponding lines to different energy values. And if you see the full width half maximum, so this full width half maximum is minimum at around 636 keV and maximum is at around 685 keV. So if you see the cursor, this is the firstly full, that is around 16,000 counts. Then we have taken the half of the count, that is around 8,000 counts. Then we have drawn a line corresponding to this, and then we plotted the line corresponding to the y-axis parallel lines and touch the energy values. And the energy for the minimum is around 636, for the maximum is around 685. So this is the FWHM, that is 685 minus 336, that is 49 keV. Now we have to calculate the resolutions, energy resolutions. So energy resolution is basically the FWHM value which you calculate. Of course, it is being done by the software. You need not to worry about it, but you should know the physics behind it. So then EO, you have to divide it. That is energy central of photopeak. So energy central of photopeak is around 661. This is the maximum peak, 661. So we divide this 49 with 661. So we get an R, that is the value responding to the percentage. So that is around 7.40 percentage. Now, these are the peak energy of gamma spectrum measured from about 661 keV of photopeak of cesium, because cesium gives you an idea of 661. Cesium is generally not practically should not be available naturally, because unless and until some nuclear fallouts are there. So, but generally cesium is given as a calibration source to all the vendors to the experimentalist, so that they could perform the calibration standards. So otherwise, naturally you will not get a cesium unless and until some nuclear fallouts are there, or there is a error in your instrument. So you should not get the cesium. So, but generally it is given by the vendors along with the instrument to perform the calibration standards. And mind it, the calibration is it's not a thing which you could understand within a single lecture, because it is very difficult. So you have to adjust voltage and current so many times to get your peaks aligned with the particular energy. So, but with your experience, and if you are having a basic knowledge of physics, you could always do the calculation and do the manipulations with the experiment, and you could adjust your instrument to be calibrated across the photo peaks which are given to you. If you see from this arrow, this is 1461 or 1460 is a peak which is corresponding to the potassium. Similarly, 1764 is a peak corresponding to the bismuth. Now, is this peak corresponding to the bismuth is basically coming from the radium. So if you see from this, radium generally we calculate in terms of 1764 keV of bismuth peak, and thorium we generally calculate into 2610 keV of thallium peak. So that is why it is very important that yesterday I gave you an idea that what are the series which you should remember, because if you are measuring what type of element, you should know that my radium is coming from, after my radium is coming, what type of peak is available to give me the gamma energy. There I have shown you some alpha, beta and gamma decays with the arrow indications. So if radium 226 is there, then the gamma peak will be coming from 214 instead of 226. So that is bismuth is responsible for giving you, because this is a gamma ray spectroscopy. It is not an alpha spectroscopy. So you should understand what type of spectroscopic technique you are using. And sometimes it is being asked also, like, sir, Uh, what is spectroscopy? Spectroscopy, if you talk in a layman's language, it's just a field where you do the analysis based upon some orderly arrangement. Now, what is spectrum? Spectrum is orderly arrangement of something. Like if I have an orderly arrangement of frequency, so I call it as an electromagnetic spectrum where there are a lot of frequencies are involved. So if I have orderly arrangement of masses, I call it as a mass spectrum. If I have orderly arrangement of frequency, I call it as a frequency spectrum. If I have orderly arrangement of energies, I call it as an energy spectrum. So you should understand that what type of performance you are performing, and if I am having a gamma ray spectroscopy, I am having orderly arrangements of the gamma rays coming out of some of the materials, and that spectrum may be absorption or emission. Again, it is a physics which is a long process, so which you basically understand, but you should have an idea that what is spectroscopy. It is a measurement or a technique which is basically used to have a study of something orderly arranged. If it is mass you are studying, it is a mass spectroscopy. If it is energy, it is energy spectroscopy. If it is a gamma, it is a gamma spectroscopy. So gamma values, if you are measuring, then it is a gamma ray spectroscopy. So this is how, by doing the FWHM values, we are estimating the E values, that is activity concentration. So the specific activities depends upon the net count rate under the piece, and then time T represents the measurement times in seconds. Then I gamma represents the energy intensity of gamma ray. Similarly, Xi is the efficiency of the detector, and M is the mass of the sample. So that is why I was saying efficiency will be different for different peaks. So you have to calculate FWHM value efficiency for every peak. Of course, you as an experimentalist, generally nowadays it is all computerized. We need not to do any calculations, but just for your basic knowledge, I am telling you that you could always calculate the efficiency for a particular energy, and then the branching intensity involved with that particular energy. There are tables available on the websites, there are tables available on the internet where you could find out that what are the different energy parameters. And mind it, my friends, you should understand the people who are working in the field of nuclear physics. The ICRP, that is International Commission of Radiological Protection, keeps a record of all the people who are working in the field of nuclear physics, especially. And it keeps the logging of all the publications which have been published by those people. After this lecture, I will tell you one example that how you could see the database that which people are working in the particular area. So you could have an idea that they keep all the records, all the tracks. If I have attended one conference, what type of paper I have presented. If I have attended, published one paper, in which journal I have published. I will show you after this lecture. Then again, yesterday, which we have already discussed, we calculate the radium equivalent and then the external or internal hazard index. And there is the next part is we can measure some radon mass exhalation and the radon surface exhalations from the soil samples also. Now, exhalation or emanations are basically two things. Exhalation means if the soil is having some radon concentration within the soil, I could also measure that radon and thoron within the soil. Like Tokonami sir was discussing lot of things, or even I have discussed in one lecture that how the pinhole cup dosimeters are used, or DTPS or DRPS are being used to estimate the radon concentration in air. But radon may be present in the soil also, because soil contains so many radioactive materials, and if that soil contains radioactive materials, So once the radioactive decay occurs, so those soils will also generate the radon or thoron. So we could select these two instruments which have been indigenously developed in India, Smart Radon Dew, which are the portable radon and thoron monitor. So it has been indigenously developed in India by the BRC with the help of some vendors, and now they are patented with the BRC. You could always go for the purchase of these instrument Radon Smart Dew, where some of the BRC people, a BRC group, are working, and they have developed this instrument. Just a very simple instrumentation is there, that there is a photomultiplier tube. So they are, after some times, after some days, the radon or the thoron is coming, and it is giving some scintillations in the scintillating material which is present, and then those scintillations are passed to the photomultiplier tubes, and then after this, the photomultiplier tubes, the diodes arrangements are there, and the counts are being increased. So you could measure the exhalation in two different modes, diffusion modes and also in the flow mode. So depending upon this, I have performed one of the case study in Shimla and Solan districts of Himachal Pradesh, and we have found that in Shimla we have selected nearly 12 samples, and in Solan we have selected nearly 13 samples. And you could see from the table that in Shimla, the radium activity gives me the maximum value of around 73 becquerel per kg. The recommended action levels are basically 30, 35 and 400. 30 for generally radium, or you could say 35 for radium, 35 to 40 for thorium, and 400 for potassium. So this is the recommended values. If they are beyond these recommended values, then it is a cause of concern. Means that soil, if you are using those as a building materials to make the bricks, or even used in the houses, that is a cause of concern. So it should be within the safe limits of 30, 35 and 400. That is radium up till 30 or to 35, potassium up till 35 to 40, and thorium to 35 to 40, and potassium up till 400 becquerel per kg. So in most of the samples, they are within the safe range, except from one or two samples. So where the detailed analysis was again designed with the help of some estimation in the water samples, estimation in the air also. So we have performed different experiments. Like surface exhalation or mass exhalation, if you see, personally speaking, if I say that mass exhalation is more important parameter as compared to the surface exhalation, because surface exhalation is not a parameter which is in your control, because this gives an idea that what type of container I am using. So if my container is little bit more flat, if you see this container, if my container is a little bit more flat, so its breadth will increase and height will decrease. So the A value, that is the surface value, will be different. Surface will be different. So if it is a skier type of a material, the surface will be different. So it is better to go for the mass exhalation to have a better idea, because mass, we know that we have used this much of soil and this is the mass exhalation. Surface is little bit depending upon the geometry, so which you need not to worry a lot. Now these are the spatial variations which we have plotted of activity concentration of radium, thorium and potassium in the soils, and you could see that the values, if it is more than 60, they are plotted in different color. If it is less than 45 they are plotted in different color in case of thorium, similarly in case of radium, in case of potassium on the upper side. And this is for the Shimla district. Green is for the radium, and this orange color is for the basically thorium, and this blue color is for the potassium. So we have spatially distributed whole of the districts in such a fashion that you could have an idea that how the grid mapping is being done. So we have mapped nearly, our lab has mapped nearly more than 70 districts till date. So where we have this spatial distribution map across all the 70 districts in the northern India, including Himachal, Rajasthan, Uttarakhand, Punjab, Haryana, and some parts of NCR also. So we have mapped a lot of districts, and our group has done a lot of studies in South also, where we have mapped some of the districts of Kerala, as well as Kalapakkam area, where our atomic power station is also situated. So you could have an idea that from this spatial distribution map, directly you could have an idea that this area, say, is a little bit more safer as compared to the dark regions. So of course, the cause of concern is if it is beyond some permissible limits, like 30 in case of radium and 40 to 45 in case of thorium, and more than 400 in case of potassium. So again, just a comparison with the bar graph, we have shown that study region average is around mentioned in Indian yellow color. It is a little bit more than the Indian average, but equivalent to the world average in case of radium. Similarly, for thorium, for potassium, the areas are matching, the values are matching with the world average. In case of radium and thorium, it is little bit more as compared to the Indian average. The reason is the geology of that area. They are the shivalics, middle shivalics, so which are having a little bit high concentrations, and it has been reported by so many workers. So this is the unscares values which I was discussing, around 30 to 35. They have mentioned 33. So that is why I have given you one range. Similarly, 45 in case of thorium and 400 in case of, or 412 in case of potassium. So these are the values which have been recommended as a average values. It should not be more than this. If it is more, still it doesn't mean that you are in danger, but you are little bit having more exposure. So again, we have done some spatial distributions by calculating the annual intake doses, and then our annual exposure in terms of civets, that is how it is affecting our body. So we have calculated and presented our results. And of course, there is a difference of exposure to the dose conversion factors for different categories of people. Like for adults, if you see the annual estimated dose, if you see the DCF values for adults, it is 0.7 sievert per gray. For children, it is around 0.85 sieverts per gray, and for infants, it is around 0.9 sieverts per gray. So you again have to use these particular values of dose conversion factors for the category of the people where you are calculating. Then these are the box plots for adults and average. And these are the conclusions. Basically, the adults, infants are the more significant radiation affected people, and among the even organs, I have mentioned that bone marrow, lungs, ovaries, testes, they are the important organs which are affected by the radiation exposure. Similarly, which I was discussing with you, that I will show you one activity in such a fashion that how those I think just a minute. I have left the meeting. Just a minute.
Hello. Sir, actually, you're not audible, sir. Your mic is mute.
Okay. Sorry. Just a minute. Yeah. Now I am audible.
Yes, sir.
Ah, so I was telling you that basically this is the agency who is keeping the track of all the things. That is the International Nuclear Information System is there. So which is keeping track of all the people who are working in the field of radiation area. So I was just telling you that you could have an idea of any person who is working in the field of nuclear science. This record is being maintained by IAEA, that is the International Atomic Energy Agency. And if you see from this, I have mentioned one of my name also, like Rohit Mehra, and you could see that I have published in these subjects. Atomic molecular condensed matter physics, nuclear materials, nuclear physics. So nearly this much of journal articles are there which have been taken as a record by those INIS references. Then publication years, you could have an idea that nearly, say, I click for 24. So these are the publications which are published in, say, 24. So you could always have a in-depth analysis of a particular person who are working, like my student Aarti is working. So this is their radiation protection and dosimetry is there. So from where it has been published, the journal is the Journal of Radionet Analytical and Nuclear Chemistry. So all the records are being kept by the IAEA. It means if you are working in this area, you are under the eyes of IAEA, Atomic Energy Agency. So say I mention another fellow of my colleague. So he is Harish Mohan Mittal, my colleague. So I will get his information, that how he is published, where he is published. So if I mention, say, my student, so I there you have to do some filter also, like one of my students is Pargan Bangotra, say. So it will give the results. So this is our paper which we have published. This is again a paper which we have published. This is again a paper which we have published. So you could have an idea that what type of publications we are doing, what type of publications the people are doing. So that gives you a basic idea of the repositories. So you could always search for those repositories. So with this, I finish my today's lecture, and if any queries are there, you are welcome.
Hello, good afternoon, sir.
Good afternoon.
Sir, I have one query that the Alara principle that is valid for the, I mean, like medical exposure, or it is also for the natural radioactivity?
It is also for the natural exposure, but for natural, actually, I have already told you. And for natural, you are being exposed by the surrounding airs around you and surrounding soil parameters around you. So
Right, sir.
that is also applicable, but exposure is less. So that was one of the protocol which we suggested while hanging our pinhole cup dosimeter, that you should keep it away from ceilings as well as the wall. Centimeter exposure comes to zero value. So it is applicable mostly in case where some radiation workers are working with the radiation sources, but naturally it is also applicable.
Okay, sir. Thank you, sir. There is one other thing is LNT model.
Mm-hmm.
So LNT model also holds for those workers, or including natural radioactivity.
That is very much applicable, but actually the problem is the purpose of this principle is to keep the radiations minimum. So the best way is you increase the distance from it, you reduce the time, because shielding is not in your hand. Shielding is within the hands of the people who are doing some things with the radiation sources. So as a layman or as a public, you can't go for the shielding. What you can do is only wear some aprons or clothes while you are going there. So shielding part is basically dealt with the people who are working in the nuclear fields, but your exposure time you could reduce, your distance you could increase, so your exposure will be lesser.
Okay. Thank you, sir. Thank you.
So any other question?
Good afternoon, sir. I have a small,
Yeah.
question. It's just on the curiosity side. If there is a nuclear war, so let's say in Europe or somewhere, maybe you say 4,000 kilometers away,
Yeah.
and the size of the nuclear bomb is maybe, let's say, 20 kilo TNT.
Yeah.
Like how we, is the radiation come over to this place, or if it comes, then how we should save it little bit, by doing some jugaad or something like that.
Like I was telling you, sir, during the discussion also, generally we don't get the cesium exposure in naturally. Okay. So cesium, if you are getting some cesium, so probably it is due to some nuclear fallouts. So one thing is the continuous monitoring which is being done by so many agencies, like in our institute we are also having a continuous 24/7 365 days monitor. So which is Radon geostation we have placed or installed with the help of BRC people. It is simultaneously done across all the places at a distance of say 100, 200 kilometers away from each other, so that within India we could cover it. So if even some activity within the range of say 80 kilometers from my Jalandhar area, suppose some nuclear activity is going on in terms of Pakistan even, so that continuous monitoring will at least detect some cesium activities. So if little bit cesium activities are on a higher side, so that is a cause of concern. So then we do some other experimentations, which is not in our control. Actually, that is a Department of Atomic Energy's problem is there. So if there is a fallout, nuclear fallout or a nuclear exposure is there, quite possible even in Russia or Ukraine war, if they use some nuclear weapons, quite possible you could have some nuclear fallouts within the surrounding areas. But your distance, I have told you that if your distance becomes double, it becomes 1/4. If it becomes thrice, it becomes 1/9. But continuous monitorings are being done by all the countries, sir.
Thank you.
Okay, ji. Then we can close this session, and tomorrow whole of the sessions will be taken by Dr. Tokonami, and day after tomorrow we will be giving you one lecture and then having some little small tests, you could say. And Biswajit, you want to ask something? Biswajit Mehra has raised his hand. So anyways, if you have some queries, we will discuss it in the next talk also. We have a continuous process of logging and recording your comments also, and we will answer those queries. Thank you once again. Thanks a lot.
Thank you, sir.